Okay, now we are going to see another topic that is called simple harmonic motion, which is simply abbreviated as SHM. It's a common topic. Those people who are doing physics, it's a bit there. But we are going to do it in terms of mathematics. We're not going to go into deep things, we are going to just do it in a case of math. So, how do we define it? This is a motion in which an object moves to and fro. So, as I can show you here, when I have this object here, this is the object. If it can move to and fro, it comes, then it comes back. It comes, then it comes back. It comes, then it comes back. That one will say that particle is describing what we call a simple harmonic. It comes, it goes back, it comes, it goes back, it comes, it goes back, okay? It comes like this, goes back, it comes, it goes back. From the point where it started, it comes, passes it, goes back, it comes, passes it, goes back. So there is that object or that particle is describing what we call a simple harmonic motion. The acceleration is always directed towards a fixed point called the equilibrium position. Acceleration is directly proportional to the displacement of the particle to the displacement from a fixed point. Equations of simple harmonic. We are going to see the definition, the common terms used in the next lesson, but now I want to just introduce it so that we know. Then when we define them, we will know what we are talking about. So, what's the particle performing a simple harmonic? Now we know what we mean by performing a simple harmonic. It means the particle is going to go below, then comes, it passes where it was, then it goes back. So this is what we call the equilibrium position. They are talking about this one. So if the particle comes, goes down, then it passes the equilibrium position up, the same distance down, then passes the same distance up. That's what we call, we say an object is describing simple harmonic. So consider, as you see, now this is our equilibrium position in that order. Now, we say x, that's the distance now, displacement covered from the equilibrium position up. But so it's going to be the same from here, up, down is also x. So when it starts from here, it drops, comes back, it goes back up there. So that's what we call a particle describing a simple motion. You see that these are the extreme ends. This distance OP is the same as this distance OP prime. So x is the displacement of the particle from the equilibrium position at time t. Then you know how we get the velocity using the differential calculus, as we said. To get velocity, we differentiate displacement. I think this one, this prime means we are differentiating displacement. And then when you differentiate displacement the second time, we shall be getting what we call acceleration. All those topics we've covered, and they are in the playlist. You go to the playlists on my channel, they are all there. Okay, then R is the amplitude. We are going to come to that next lesson. Velocity reduces as the particle moves away from the equilibrium position up. Velocity from here, the velocity is going to reduce. So the velocity of this particle is at maximum when it's heading towards O. But if it's going away from A to these extreme points, it means that it's going to be reducing. But acceleration increases as the particle is going towards this side. So that is the case. Acceleration first is increasing when we are going to extreme ends. The particle moves to instantaneous rest at P and O. Now, note, when this particle is going down, then comes back. At this point, before it comes back up, there is that time before when it's tending to come back, its velocity there is always going to be 0. Whenever it goes, then this time before it comes back, there at that point the velocity is 0. So the amplitude of P equaling to OP prime, this amplitude, this is what we call the amplitude. Okay? Amplitude is the maximum displacement of the particle from O. From here, it's the maximum the particle can be displaced. okay, from O, and you know that you say that acceleration is equal to differentiate displacement 2 times, and you say it's proportional to the displacement from the fixed point. So you have that, and remember whenever you have this, we introduce a proportionality constant. This one can say that from circular motion, this is called omega. Now, we are introducing this as a negative omega squared for simplicity. When we are going to interpret the thing, but we are introducing this just for simplicity, to simplify life. So don't ask where is it coming from. We are introducing a negative and omega squared for simplicity, but it's a constant. Like whenever you remove a proportionality constant, you can introduce K, you can introduce C, up to you. But now we are introducing this just because of our next work we are going to see when we are integrating and removing that constant. So it's easier when we introduce it as omega squared, but the negative as you are going to see. Now, remember we say that to get displacement from calculus, from differential calculus, you say to get displacement, you differentiate velocity with respect to time. I mean to get acceleration, you differentiate velocity with respect to time. But this acceleration we are having, remember this one, acceleration is equal to when you differentiate displacement to time. But we said also the same acceleration is equal when you differentiate velocity with respect to time. Now, because I'm having this as a function, I mean this as x, the displacement is in terms of x, then I can use the chain rule so that this one is going to be dv dx, then I introduce dx dt. And so when I simplify this, this is going to be equal to that. But whenever I differentiate displacement once, you'll be getting velocity. From here, whenever I differentiate it once, you'll be getting velocity. And so when we put in that velocity, then here, this is what we have. So the whole of this is equal to v dv dx, which I substitute now from here. I put it there. And now separate variables. I take this side. Separating variables means you take the functions of x and the command to one side, and you leave this side. So we have v dv. So you have x, I also take the x the other side. When that's the case we have, then we interpret both sides. When you interpret this, we increase the power by 1, divided by the new power. So this one is the power 1. Increase the power by 1, divided by the new power. When you increase this by 1, you get 2, divided by 2. The same here, x squared over 2 plus a constant of integration. Now, when v is 0, when do we say v is 0? We say that when these particles at this extreme ends, when it at this side, before coming back, velocity is 0. But this velocity is 0 when it has covered a distance or either of this or this. These are the distances it has covered here. Okay? Either from here or from here. Up is positive, below is negative. So that's why we said when v is 0, the distance covered here, the amplitude is going to be plus or minus. For minus, when it's going below, positive when it's going up. So I think you know why it is 0. That when this particle here goes down, before it comes back like this, it means that the velocity at that point of time to come back, velocity is 0. But it has covered a displacement which is equal to r. Okay, so that's when we put in the condition. Initial conditions to get this C. When I take now this side, I think you see now. When I take this side, it's a positive. That's why we chose a positive with the is. Then when I take it this side, I think we see we get positive equal to C. So that squares are common. As you can see, squares are common. That's why we also chose this one to be a square, the proportionality constant. So in there, you can see, when I introduce now where is C, here, I'm going to put it here now because I know what C, the proportionality constant, and then what the integration constant is. So putting it back there, and you simplify, you see multiply through by 2 because 2 is common, so multiply through by 2. Then I start with this here, then I end with this here. I think it's that omega squared is common. Factorize it out, and then have the velocity equally at that. Now, we said at O, the equilibrium position. This one, the equilibrium position O. At V is at its maximum. We said Velocity is going to increase as this particle is heading towards, or from here it's heading towards, or we say the velocity is going to be at its maximum. But if it's at its maximum, from here, because we assume this is our starting point, it means at this point, the particles covered zero distance. That's why then we come and substitute in 0. Displacement is 0 at that time. So we have now this squared max equal to 2 omega squared r squared. Get the square root, we are having that. So that's the formula that we are going to always use when we are getting the maximum velocity of that particle. So from this still, from that thing up, we have this. If I take the square root of this is omega, this and then I have a square root. Remember, I'm going to get a square root to get plus or minus. So, case 1, let us consider when this is positive. We separate. You know that our v, this one is in terms of x. This displacement is a constant. So the variable is x because it's the displacement and it's going to change. So it's still like you say v is equal to this. So where this v, I put this. Now that calls for separating the variables. Bring x this side, I take the t the other side, so that I have that. Then from there, the next thing I'm going to interpret. I think we said whenever I have a square root of r squared minus something squared, then on kind calls for interpreting of sine inverse or sine substitution. We saw those also in the pure mathematics, and the priests are there also in integration. You can go and list them and you see how we handle, how we interpret these things here. Whenever you interpret this, you get something like that. Now, when you interpret this is a constant, you interpret the t, here being t, then plus the phase constant. This one we call it the phase constant, as we are going to see in the next lesson there. So, sine inverse, when I take now that inverse back the sine, if I take this inverse, the sine, then I'll be having x over r equal to the sine, adding it there like that, which is going to be, then I cross multiply this r to come there. That's what I call it. Now, this is a function, displacement is a function of t. Simple. Phi is a phase constant. Case 2. When we have now this as a negative, you separate the variables as you see. This negative is going to come this side, then this one is going to be a positive. And whenever you have this as a negative, and interpreting this, there you are going to get cos inverse. I did also that thing in pure mathematics, and the videos are there in integration. Just visit the playlist and see, go through them. That's why here I'm just going through. This one, when you interpret this is the constant, so interpret this, you get t plus sigma, which you also call a phase constant. Then when you put this beside, you get this and multiply this, you get that. So now in this lesson, we are going to see how we draw these two, and then from there, how do we remove these phase constants, and then we give the common terms when we are basing on those two diagrams. So that's it. I wish you well. Please don't forget to subscribe to the channel. For contacts, contact me through those contacts.